Okay, this is our second video of problems from class. This one I didn't get to, I don't think. No, I didn't. In class, this is a modified Atwood. So remember, with this scenario, we've got one mass on top of a table, and then it's connected to another mass via a string that loops over a pulley. Our string and our pulley are frictionless and massless, and in the case of this problem, we actually do have friction on this surface. So, quick free body diagram. This object has force of gravity and normal that are the same. It's going to have a tension pulling this way, and it's going to have a force of friction in the opposite direction. And then my hanging mass has got a force of gravity and then a tension pulling back up in the opposite direction. And I'm defining my coordinate system as positive x, okay, in the direction of the mass that's hanging, because once we let this go, it's going to be pulling this mass along, okay. Okay, so we're actually given the force of gravity on these two boxes. This one is 10 newtons and this one is 30 newtons. And then we're given a coefficient of friction of 0.2, and we need to find acceleration. So we'll reference our handy dandy sheet. I've gone through how to derive this in another video, so I'm not going to do it in this one. But for our modified Atwood, if we have friction, then this is going to be our acceleration. It's the force of gravity of the hanging box minus the force of friction divided by the sum of the masses. Okay. So I'm going to write that down. Okay. I need my masses, right? I know that this is 30 newtons because they gave me that already as a force, but for these individuals and then for this force of friction, I'm going to need to get my masses. So just remembering force of gravity is mass times g. If this one is 10 newtons, okay, 10 equals 9.8 times whatever the mass of this one is. This mass is going to be roughly 1 kilogram because I'm dividing 10 by basically 10. And then my other one is going to be roughly 3 kilograms. So I'll say that one's mass 2, the one on the table. Actually, no. Mass 1 is the hanging one, and mass 2 is the one on the table. That's the way I've been trying to do this. So, okay. So we've got our 30 newtons. We can use the 30 here because that's the same 3 basically times 9.8. For force of friction, we've got our coefficient of friction times our normal force, and that's going to be the same for this object as the force of gravity because they're offsetting each other. So I'm going to have 0.2 times, 0.2 times 10 for this one. And then I'm going to divide that by 3 plus 1 for the sum of my two masses. So 3 plus 1, I'm going to divide that by 4. Okay. So I've got 30 minus, my calculator is on 30 minus 0.2 times 10. And I'm going to divide that by 4. That gives me 7 meters per second per second. And so my answer, the closest one to 7 is D. Okay. Okay, wrecking ball. I did this one, I think, in both classes today, but my wrecking ball, it's connected to 2 cables. Okay, so we've got a T1 here that's horizontal. We'll call this a T2. And we want to know what T1 is. We know our wrecking ball has a force of gravity, and we're given that already because we're given its weight, which is 2,500 newtons. And we know it's pulled to an angle of 70 degrees. That's all we know, but that is enough for us to figure out the values of these tensions, okay? We know this is balanced, okay? So again, similar to the one from the first video, we're going to look at some components. We're going to have force of gravity equal to the y component of this T2. And we know that's also equal to 2,500 newtons, okay? Then we know that T1 has got to be balanced on this other side by T1x. Okay, so we are going to use tangent, which remember is opposite over adjacent, to help us out here. Tangent is going to be, if the tangent of this angle is going to be my T2y, which I know, over my T1x, which I don't know, and which I want, because that'll give me the answer I want. So tangent of 70, and that's my opposite side over my adjacent side. Remember, tangent's the one that doesn't use the hypotenuse, okay? Actually, that's T2x. I don't want to keep writing a 1 there. I guess because that's T1. Okay, so I shift this around. T2x equals T2y divided by tan of 70, which also equals 2,500 newtons divided by tan of 70. And then that's going to give me right at 910 newtons. Okay, and so that is my x component of T2. That's also the same as T1. So that's my answer. It's 910 newtons. Okay. All right, next one. I did this one for, I think, third period, but probably not first. So 2 football players. They've been pushing this blocking sled. I'm going to be honest and say I really don't know what that is, but it's some kind of big thing. So they've been pushing it across the field. Where we're thinking about this scenario starting is where they've been pushing it, they've let it go, and so it's moving at a constant speed of 2 meters per second, and that constant's a little misleading here, okay, because it's really not constant. It's really going to be slowing down because there is kinetic friction between the grass and the sled. So eventually, this thing is going to come to a stop, because imagine you give something a push and then you let it go and it moves along until friction makes it stop. That's what's happening here. This thing is moving along the ground and eventually friction is going to make it stop. So it's really going to be slowing down. Okay. We want to know, once they stop pushing, how far is it going to continue to slide before it comes to a rest? So we really are wanting displacement here. Okay, so this is another one where we're going to combine kinematics and forces. So start off with F net. Our only force acting is friction at this point. Okay, we're not thinking about the push they gave it. Our scenario is starting after they gave it the push and it's moving along, but it's slowing down due to friction. So F net equals force of friction. That equals mu times our normal force, which equals mu times mass times g, because this is on horizontal ground. So F of g equals F of n. So that's going to give me, let's see, 0.3 times 60. That's our mass. Yep. Times 9.8 is 176.4 newtons. Then I can get my acceleration. That's 176.4 newtons divided by my 60 kilogram mass. Okay, so I'm going to get 2.94 meters per second for that. And I'm going to give that a negative value because it's slowing down. Okay. And now I can take this and put it into a kinematic equation. I know that I'm starting off at 2 meters per second, and I'm going to be slowing down so that my final velocity is 0. So I've got initial, final, acceleration. I need displacement. no time information in here whatsoever. So I'm going to look at, of these equations, I'm really going to look at having to use this one because I don't know anything about time. I don't really have a choice if I don't have time. So VF squared equals VI squared plus 2A delta X. I'm going to substitute values. I've got 0 for my final velocity. I've got 2, that's going to be squared for my initial velocity, plus 2 times a minus 2.94 times my displacement, which is what I'm solving for. Shift this over, this becomes 4 because that's 2 squared. And then when I move it over to the other side, or I subtract it from both sides, I got a minus 4 over here equals minus 5.88 is what I got multiplying these two. That's times delta x. And then I solve for delta x. I ended up with 0.68 meters. So that's B. Okay. Okay, one more video after this.